Okay, good morning all. So this is our 20th lecture of the course Compressible Flow and Gas Dynamics. In the previous lecture we have started our discussion on the interaction of shock waves, and if you do remember we have completed the interaction of shock waves for waves of opposite families. Today we will start with interaction of shock waves of same family. So what we will try to do, we will try to consider over here the left running shock waves, and if you do remember I have already included the already started the portion of left running shock wave. So what we have done, we considered that I have a surface and then I have nothing but a concave corner. Okay, so at this concave corner what will be happening, I know I will be having formation of nothing but an oblique shock wave. Now let's consider this oblique shock wave with this particular concave corner is making an angle of beta. Okay, so beta is the angle which it is making. Now if I consider that at some point A I have nothing but formation of a Mach wave. So I can easily consider the formation of Mach wave over here, because on the downstream of the Mach wave there will not be any changes in the properties. Okay, so Mach wave is nothing but a weak shock wave. So let me consider over here that I have nothing but a Mach wave over here, and this particular Mach wave is having angle mu1. Okay, similarly, say this is my point B. Similarly, in the downstream also I am considering that I have a Mach wave, and let's consider the angle of this particular Mach wave is nothing but mu2. Okay, and this theta is actually our flow deflection angle over here. Okay, so now if I consider a streamline, say I have a streamline that is approaching with Mach number 1. I know Mach wave is a weak wave, so nothing will happen over here. This streamline will keep on continuing. Once it faces this oblique shock wave, it will deflect through angle theta, and here Mach number will become m2, and once again if I have this weak Mach wave, then nothing will happen over here. Okay, I know from my earlier analysis that if I have my velocity which is coming over here as v1, it will be having some normal component vn1 which is normal to this oblique shock wave, and as per the trigonometric relations, this sine of beta will become nothing but Vn1 divided by V1. Similarly, this is a Mach wave over here. For this Mach wave also, what I can do, I can write it in terms of the Mach angle. Okay, so if you see, I know that Mach angle, sine of Mach angle mu1 is nothing but equal to 1 by Mach number. So in this region our Mach number is m1, so it will be 1 by m1, and m1 I can write v1 by a1, so this will be a1 by v1. So these two relations I have now got over here. So this one is for the Mach wave, and this one is for the oblique shock wave. Okay, so now if we see particularly this oblique shock wave will be forming only if I have nothing but the supersonic flow. Okay, and for supersonic flow to occur, what has to happen, the normal component of the velocity Vn1 has to be greater than speed of sound. So for this normal shock wave to occur, the upstream normal velocity of the shock wave has to be greater than the speed of sound. So from here I can tell that this magnitude of Vn1 by V1, so because in the denominator V1 is same, so Vn1 by V1 will be greater than A1 by V1. So as my this entire magnitude is greater, so from here I can clearly say that beta has to be greater than mu1. Okay, so it means that if this is my angle beta and this is my angle mu, then it can be clearly said that if I have a Mach wave over here, that Mach wave has to ultimately interact with this particular shock wave over here, because its angle of Mach wave is less. Okay, so if it is at higher angle than beta, then it will not meet even up to infinity with this shock wave. But as its angle mu is less than angle beta, so if any Mach wave is originating at point A, that will always interact with an oblique shock wave which is starting from point B having angle beta which is greater than mu1. Okay, so this is one point, that if I consider any Mach wave in the upstream direction, ultimately that has to interact with this particular oblique shock wave. Now let's consider in the downstream direction. Okay, so the downstream direction, like m2, I will be having velocity vector also over here, say v2. Okay, and if I see this particular velocity vector v2, so with horizontal it is making angle theta, and this particular wave with horizontal is making angle beta. So with reference to wave, this angle is nothing but beta minus theta. Okay, so ultimately I can say that sine of beta minus theta will be equal to Vn2 divided by V2, and from particularly for this Mach wave, now it is in the downstream direction, so my flow Mach number is m2. So for the downstream of this oblique shock wave, my Mach number is m2. So in the downstream, I can say that sine of mu2 will be equal to a2 divided by v2. Okay, so now we all know that if I have the presence of an oblique shock wave, so I will be finding that downstream Mach number m2 will be less than 1. So it means in the downstream I will be having nothing but the subsonic flow. Okay, so if I have subsonic flow over here, what ultimately will be happening, this a2 has to be greater than Vn2. Okay, so if a2 is greater than Vn2, I can say that Vn2 by V2 will be less in comparison to a2 by V2. Okay, and considering this fact, I can simply say that angle beta minus theta will be less than mu2. Okay, so mu2 will be greater than angle beta minus theta. Now let's come to this diagram. So if you go to this diagram, this angle with horizontal is beta, this angle is theta. So ultimately the shock wave is making an angle of beta minus theta with this particular direction. Now this is my angle mu2. So you can see that this mu2 angle is greater than angle beta minus theta. So if I have this mu2 angle which is greater than beta minus theta, so ultimately what will be happening, whatever this Mach wave is producing at this point, this will interact with this, nothing but the shock wave which is originating at point B. Okay, so one important conclusion, so any Mach wave I have in the upstream of the oblique shock wave, that will be having angle less than the angle of the oblique wave, so it will actually intersect with the oblique shock wave. Similarly, any Mach wave which is on the downstream of the oblique shock wave, that its angle will be greater than the angle of the corresponding oblique shock wave, so we will be finding it will also be interacting with this particular oblique shock wave. Okay, so with this understanding, let's now try to consider a situation where we are having nothing but two shock waves of the same family, and let's try to make the physical inferences that how these will be interacting. Okay, so what I will consider now, I will consider that I have some corner which is having angle theta 1. So this angle is theta 1, and then say this is my point A, then this is my point B, and at point B once again I am having some another corner. Okay, and this is making say some angle theta 2. Okay, so now ultimately what will happen, I will be having a oblique shock wave over here at point A, because this is a concave corner. So at this concave corner I will be having nothing but a shock wave over here. Okay, so let's consider the angle made by this shock wave is beta 1. Fine. Now this is my point B. So at point B also I will be having nothing but formation of another shock wave. Okay, and before that let's understand that if I have flow Mach number in the upstream of this as m1, then I will be having flow deflection theta 1 over here, and this Mach number will become m2, and ultimately this m2 will be less than m1. Okay, so m2 will be less than m1. So now if I see, if any wave which starts at point B, I have already seen that after the deflection, if I have the presence of a wave, then beta minus theta is less even than the Mach wave which is forming at point B. But because point B is having sharp corner, so I know here despite of Mach wave I will be having formation of a another oblique shock wave. Okay, and as I know that the presence the strength of oblique shock wave is greater in comparison to the strength of the Mach wave, so I can say that angle beta 2 will be greater than mu 2, because mu 2 I am considering that if I have the presence of any normal any Mach wave over here, so the angle for that particular wave at point B will be mu 2, and because it is having sharp corner, so despite Mach wave, here I will be having presence of another oblique shock wave. Okay, so if I have another oblique shock wave over here, because the strength of oblique shock wave is greater in comparison to the strength of the Mach wave, that's why this beta 2 has to be greater than mu 2, and we know that just now in the previous discussion we have concluded that this mu 2 is greater than beta 1 minus theta 1. So this angle is beta 1 minus theta 1. So if any wave will be producing, Mach wave will be producing, that will be having angle mu 2 which will be greater than this beta 1 minus theta 1. But ultimately what is happening over here, ultimately here an oblique shock wave is producing, so ultimately this beta 2 will also be greater than beta 1 minus theta 1. So it means that now I will be having another shock wave over here, and this shock wave, when it will make an angle with this particular direction, okay, so this angle will be my beta 2 angle. Okay, and beta 2 angle will be greater than beta 1 minus theta angle. Okay, so up to this point is it clear? So what I have now, you can see that this is my first shock wave, then from point V second shock wave is starting, and this second shock wave is making angle beta 2, and this angle is greater than beta 1 minus theta. So angle of this wave is greater in comparison to angle of this initial shock wave. Okay, so this is the reason that I will be finding this wave will actually interact with this earlier originated oblique shock waves. And another important point here, you can see both the waves are of nothing but the same family. Okay, so these two same family waves are interacting, say at point C, and after point C, say these are originating as a single these are going as a single wave. Okay, so now say this is my point D. So I am saying that after the interaction of these two oblique shock wave, these has formed nothing but a single, these has propagated as a single shock wave as CD. Okay, now if you see, this is the region 1. After region 1, this is my region 2, and then here also I will be having another oblique shock wave I am having. So here I will be having more deflection. So say this is my region number 3. Okay, and in this particular region you can see that flow is starting at point 1. If I see in portion CD, in portion CD also flow is starting at point 1, and then this flow is also say deflecting. Okay, so ultimately what is happening, ultimately you can see over here that this flow which is in the upstream of the ACD, that is having same conditions which is equivalent to that of Mach number 1. Now below point C, what is happening, first this flow is deflecting through the wave AC becoming Mach number M2, then it is deflecting through wave BC, and then it is becoming Mach number M3. Whereas in the first case what is happening, for this particular wave CD, it is only passing through a single wave. So this is very clear to us that we know that an oblique shock wave nothing but results in change in entropy of the fluid medium. It results in change in stagnation pressure. So we will be finding that the changes in entropy and the changes in stagnation pressure for this particular wave, which is wave CD, and the flow which has gone through waves AC and BC will be actually different. So in this zone, my properties M3, if Mach number is M3, here Mach number will not be identical to M3, it will be different. So let me call this as nothing but region 4, and my Mach number is corresponding Mach number is M4. And because here the flow is facing only a single shock wave, here flow is facing two shock waves, so changes in their properties will be different. Okay, so this point is very clear that below point C I have nothing but region 3, and above point 3 I have region 4. So some of the properties in region 3 and region 4 will be different because changes in entropy of the fluid medium is actually different for these two regions. Okay, so I have to consider that point C is nothing but considering a line which demarcates the, or which represents the discontinuity between the properties. So let me also name this as CE. So I am considering point CE over here is nothing but a line that is creating actually discontinuity between the properties at point properties in region 4 and properties in region 3. Okay, so this particular line I will be calling as nothing but the slip line. Okay, but we have also seen in our previous lecture that if I have the presence of slip line, then in the upstream and downstream of slip line, so if I have, say, this is above slip line region 4 and below slip line if I have region 3, so ultimately for a straight slip line to exist, P3 has to be equal to P4. And another important point is that because this particular slip line will be existing only if flow direction is also same. So if this is deflecting, say, at an angle theta 2, and if this is deflecting at an angle theta 3, then ultimately theta 2 has also to be equal to theta 3. Okay, but this is passing through a single wave and this is passing through two waves. Okay, so obviously it is not possible to maintain the same set of properties over here in region 4 and region 3. So this necessary condition which is necessary for a straight slip line to occur, it is impossible to achieve in this situation because here the flow is passing through a single wave, here flow is passing through set of two waves. Okay, so ultimately I cannot ensure that both the properties pressure as well as theta are being maintained at the same point of time. Okay, so I can create some situation where only a single condition can be satisfied when the flow is going after two waves and single wave, but satisfying both the conditions at the same point of time is actually practically not feasible. Okay, so what happens basically, the nature itself tries to adjust this particular necessary condition, and in an attempt to adjust this condition, nature creates a reflected shock wave from point C. So here I will be having from C to F nothing but a reflected shock wave. And once you have this reflected shock wave, so when the streamline which is starting and moving along this direction, when it will be interacting with this reflected shock wave, it will actually bend further downwards and becomes parallel to nothing but slip line, which is parallel to this above streamline. And this angle, if it is say theta 4, I will be able to find that my theta 3 is equal to theta 4. Okay, and another interesting point is that this reflected shock wave will also adjust the pressure condition. So if I say that after this reflected shock wave, over here I have nothing but region 5. Okay, so in this region 5 I will be finding that pressure will be equal to, static pressure will be equal to that of the static pressure in region 4. So ultimately I will get this point also, that P4 is equal to P5. Okay, so this is the important point, because the flow which is passing through these two shock waves and the flow which is passing through single shock wave in the downstream cannot create a situation where both pressure and theta conditions are satisfied, which are necessary for a straight slip line to occur. Okay, so what will be happening, ultimately the nature will create one more reflected shock wave over here, and this particular reflected shock wave will be created at such an angle so that ultimately my flow is deflecting at an angle theta 4, which is equal to theta 3, and the pressure in region 5 becomes identical to that of the pressure in region 4. So P4 is equal to P5, which is required to maintain this straight slip line condition over here. Okay, so this is how we can say that the two shock waves of same family actually interacts. Okay, so here you can see this is one corner, this is another corner. So these two will be interacting, then starting a single wave. But while these are starting a single wave, ultimately one reflected shock wave has to come in order to create a slip line over here. And this particular slip line has to satisfy the condition that above the slip line and below the slip line flow velocity is in the same direction, so streamline is in the same direction and pressures are the same. So ultimately what happens, basically when we do solve this type of interaction of the shock waves of same families, we have to follow an iterative procedure, and as per the iterative procedures we have to adjust the angles of waves CD and CF in order to reach this necessary condition. Okay, so this is important point. Let me repeat it again. When we solve the interaction of two shock waves of same families, ultimately what happens, these shock waves nothing but has to satisfy this condition. So to satisfy this condition, iteratively we change the angle of this oblique shock wave CD and reflected shock wave CF, and we adjust these angles to create a situation such that in the downstream of these two waves we have nothing but this particular condition satisfied. Okay, okay, so this is very important point regarding the interaction of the shock waves of same family. Now let's also try to consider a situation that in place of a sharp corner, if I have nothing but gradual concave corner. Okay, so what will happen for gradual concave corner? So what I am trying to say is that I have a situation something like this. Where the profile of the surface is not changing sharply, but it is changing gradually. However, ultimately if you see, this is the one direction and this is the another direction. So ultimately it is deflecting through angle theta only, a finite angle. So this theta over here you can see is finite angle, and if you extend this two lines, this will form a sharp corner also over here, but we don't have sharp corner. As per the geometry, we are having nothing but the gradual variation of the flow. Okay, so in this type of situation, we know that I will be finding a flow streamline which will be something like this, which will follow completely the flow and then becomes something like this. Okay, so this is my say flow streamline, which is starting at Mach number 1 and then finally becoming Mach number 2, because it is deflecting through this gradual through finite angle theta, but in a gradual manner. Okay, and ultimately what will happen in this whole process, we will be finding that variations of the properties will not happen. So in discontinuous manner, property is varying, but variation of property is happening in a continuous manner. Okay, so how to physically create this situation with the shock wave conditions, let's try to understand. Okay, so if I just take this portion, say this is my curvature portion, and if I zoom in this curvature portion. Okay, so if I zoom in this curvature portion, so let me zoom in it in the next slide. So what I am saying is, say I have this curvature portion over here, so I am actually trying to zoom in this. If I zoom in, I will be finding my curvature something like this, and ultimately what I can do, I can create this as nothing but combination of multiple deflection angles. So what I have done, basically I have a curve. This curve I have fitted with small lines, and each line is showing some angle, say some deflection angle. For example, here this was coming straight, so after this angle, deflection angle is say d theta 1. Then it was going in this direction, and then I have deflection over here, so say this angle is d theta 2. So I have whole curvature I have divided into nothing but small theta i's, and these theta i's of infinitesimally small deflections. Okay, so when I have a finite deflection theta, then I have the presence of nothing but a shock wave which is having angle beta. If I have infinitesimally small deflection, then what I will be finding? I will be finding a shock wave, but that particular shock wave will be of very weak shock wave. So its strength will be less. And this type of if I take this infinitely small deflection, so d theta is infinitely small, so it means that my shock wave will also be of infinitesimally small strength. So such type of weak shock wave will be nothing but a Mach wave. Okay, so it means that if I have a gradual deflection, in this gradual deflection, what will be happening? I will be having formation of, because it has deflected through this angle d theta 1, and this d theta 1 is nothing but infinitely small. Okay, so because of this infinitely small angle, I will be finding that I will be having formation of a wave over here, but this will be nothing but a Mach wave. Okay, then at this point I will get another Mach wave. However, in this portion my Mach number, say if my initial Mach number is m1, and across this shock wave dm1 is the drop in the Mach number. So my new Mach number after this shock wave will be m1 minus dm1. So I have slight decrease in the Mach number. So this decrease is also infinitesimally small. So if this decrease is small, now whatever the new shock wave will form, this is experiencing a Mach number of m1 minus dm1. So it will be having slightly more Mach angle. So if it is having slightly more Mach angle, it will be moving something like this. Then another Mach wave, but that will be having slightly more Mach angle. Okay, so this we have seen earlier also. In our first slide I have told you, in the downstream direction, as I keep on moving in the downstream of a shock wave, my angle of the Mach wave will keep on increasing. So that is what I am doing over here, as I am saying that though I have infinitely weak shock wave, but with this infinitely weak shock wave also I will be having very slight decrease in the Mach number. So this very slight decrease in the Mach number will keep on creating a situation where my wave angle is actually, Mach wave angle is increasing. So in this type of gradual deflection, I am getting nothing but a series of Mach waves. And as we know that a Mach wave is a weak shock wave or infinitesimally strength shock wave, so it will not create any discontinuity in the property. So properties will slightly change, but these will change in nothing but continuous or gradual fashion over here. Okay, so this is the zoomed view. So it means in the original picture, what I can do, in the original picture now I can create the combination of waves over here. So I can say that, say this is my one Mach wave, this is my another Mach wave, then another Mach wave, and as I am moving in the downstream direction, this angle is actually keep on increasing. So this angle of Mach wave is actually keep on increasing. Okay, so ultimately this will reach and saturate at this point. Okay, so in this bottom portion I have nothing but series of Mach wave. So through each Mach wave there is very small change in the property of the fluid medium, but this change is happening in a continuous manner because I am having over here the combination of, so in reality you will be finding that I will be having nothing but infinite number of Mach waves over here. Okay, and these infinite number of Mach waves, the angle of the Mach wave will keep on increasing as we move in the downstream direction. So these number of Mach waves will actually intersect at a distance sufficiently far away from this solid boundary, and once these have interacted, after their intersection point, these will form nothing but a oblique shock wave over here. So all these Mach waves are joining together. Okay, these are intersecting at this point. So if these have intersecting at this point, whatever the strength of the individual wave is there, that has actually accumulated, and now this will form over here an oblique shock wave. And you will be finding that if a streamline which is passing through this oblique shock wave, that will ultimately become parallel to the streamline which is passing through the series of shock waves, but above this point I will be having nothing but discontinuity in the variation of property. So suddenly within this oblique shock wave region, my Mach number has transformed from m1 to m2, and flow direction has changed from this horizontal direction to this particular direction, which is aligned at an angle theta. Okay, so in this region which is sufficiently away from the wall, I am having nothing but sudden variation in the properties, whereas the region which is very close to this, which is very close to this particular boundary over here, which is actually gradually changing, in this region I am having nothing but the gradual variation of the property. So ultimately I can say that if I have the presence of a gradual concave surface, for this gradual concave surface, near the surface I will be having the presence of infinite number of Mach waves, and these Mach waves will lead to gradual variation in the flow properties, whereas when these Mach waves will actually intersect with each other at distance sufficiently far away from the surface, after their interaction they will form nothing but an oblique shock wave, and the flow which is passing through that oblique shock wave, that will be having sudden or discontinuous variation in its properties, and ultimately the properties whatever becoming identical to that of this series of shock waves, these will try to attain the similar values over here. Okay, so this is how we can actually analyze a situation if I have a gradual concave surface. Okay, now let's try to extend this type of analysis for the convex surfaces. So first let me give you idea about the gradual convex surface only. So say this is a gradual convex surface over here. So ultimately I know that my flow streamline will also be parallel to the surface and moves in a continuous manner. Okay, so I can say that over this surface I have nothing but formation of multiple Mach waves. And now the flow becomes parallel to this particular direction. Okay, so in this situation what you will be experiencing, that if you are having a gradual convex surface, though you are having the presence of large number of Mach waves, but these Mach waves will never intersect. These will never intersect. Okay, because as you move downwards, angle will be keep on changing and this will be keep on diverging actually. Okay, so these will not meet even up to infinity. So here I will be having always the gradual variation of the flow and I will not be finding the presence of a shock wave. Okay, now if you consider a sharp convex corner, so for a sharp convex corner, I will be finding that so this angle is theta. So for a sharp convex corner, I will be finding that any streamline which is just adjacent to this surface, that particular streamline has to have discontinuous variation in property and discontinuity in its flow direction, whereas all the streamlines which are away from this sharp corner, these can actually move in a gradual fashion and then reach to new situation. Okay, and then adjust to new flow direction. I can have this type of situation, but a streamline which is just adjacent to this surface, it has to change its direction instantly. Okay, and there will be sudden changes or discontinuous changes in its properties. So basically you have seen in case of a gradual variation that I have nothing but the combination of multiple Mach waves. So ultimately what happens for a sharp corner here also, because in this region the variation in properties is gradual, so it means this has to pass through a combination of multiple Mach waves. Okay, but at this point all the Mach waves are meeting and creating nothing but a high strength. So that is the reason that at this point whatever the streamline which is passing through this point, that particular streamline has to go with the sharp change in its property. Okay, so here you can see that I have combination of or infinite number of waves over here, and as I told you that away from this surface the variation is nothing but continuous over here, because flow streamline adjusts in a smooth manner. Okay, so if this variation is in a gradual manner, so it means that all these waves which we are finding over here, these waves are nothing but our Mach waves, or these are also called as expansion waves. Okay, and I will be having one starting expansion wave over here. So this starting expansion wave is called as forward expansion wave, and ending expansion wave is called as rearward expansion wave. Okay, and ultimately I have this forward wave which is facing an angle of which is facing a Mach number of m1. So corresponding to this my angle will be mu1, which is equal to sine inverse 1 by m1. So angle of this initial shock wave, that is initial expansion wave, is nothing but my mu1, and this last wave is nothing but having flow Mach number in the downstream direction as m2, so its angle mu2 will be sine inverse 1 by m2. So this angle over here will be nothing but my angle mu2. Okay, and whatever the region I am having which is bounded by this forward expansion wave and rearward expansion wave, and which is the combination of the infinite number of expansion waves, this particular region is called as nothing but the expansion fan. Okay, so the region over here which is a combination of which includes the large number of expansion waves, so that particular region is called as an expansion fan. Another interesting feature is that if you see all these expansion waves, these are meeting at a corner. Okay, so this type of expansion waves are also called as cornered expansion waves. Okay, so I am having expansion, and this expansion is creating the some weak waves which leads to continuous or gradual variation in the properties. So this is the reason these are called as expansion waves. And another point is that because all these expansion waves for this sharp corner are meeting at this point, so this is the point from where these are originating, and the reason for meeting at this point is that all these waves will create nothing but high strength point over here, and this high strength point will lead to sudden change in the properties of the streamline which is just adjacent to the solid boundary. Okay, and away from this, because this zone is, these waves are expanding, so ultimately what is happening, if you can see here I have sudden variation, then any streamline which is passing through this section, that is having this much zone of this much angular zone over which actually properties are varying, and as I am moving away from the corner, then I am having actually more wider zone through which actually gradual variation is taking place. Okay, so ultimately what is happening, all the expansion waves are actually originating from same corner, but ultimately their angles are different. So as these are moving away from the surface, these are actually diverging, so finally these expansion waves will never meet. Okay, so only these are meeting at a single point. So this is the reason these are also called as cornered expansion waves. Okay, so this type of flow situation where we are having nothing but the one expansion we are having the expansion of the flow taking place. This particular flow was first analyzed by a student of Prandtl whose name was Mayer. So this is the reason that this particular flow situation is also called as Prandtl-Mayer flow, and the wave is also known as Prandtl-Mayer expansion wave. So these are also called as Prandtl-Mayer expansion waves. Okay, so Prandtl sometimes in 1905. So if you see Prandtl, he is famously known for his works related to the boundary layer phenomenon, but in year 1905 or 1906 he has also done some work which actually predicts the thickness of the shock waves for some specific situations, and then his student Mayer has extensively worked on the flow through this expansions, and his doctoral thesis was completely on this work. So this is the reason that it is also known as Prandtl-Mayer expansion waves. Okay, now we generally call the flow situation which is passing through this particular corner as nothing but the Prandtl-Mayer flow as well. Okay, so let's try to see some of the characteristics of the Prandtl-Mayer flow. So one interesting point is that I have a sharp corner, okay, and then I have, from this corner I have the formation of a expansion fan, and that expansion fan is having some forward wave which is making an angle mu1, and it is having one rearward wave which is making an angle mu2, and this, in between this region I have nothing but an expansion fan or Prandtl-Mayer expansion fan. Okay, now any flow streamline which is passing through this region is, say, having Mach number 1, then this will gradually expand, and ultimately I will be finding that in this region my Mach number is m2, and as it is passing through the series of waves, so we will be finding that we will be having changes in the flow properties. Okay, but ultimate thing is that in many ways this particular expansion fan is nothing but completely opposite to that of a shock wave. Okay, so let's try to see what are the opposite behavior. So first opposite behavior is that m2 will be greater than m1. So through the expansion fan we will be finding that we are having increase of flow Mach number. We have seen that a shock wave decreases the Mach number, but here we will be finding that we will be having increase of flow Mach number. Second important point, if you see, we have observed previously that in the downstream of the shock wave we are having nothing but increase in the property values. For example, pressure, temperature, density increases, whereas for the case of expansion waves, rho 2 by rho 1, P2 by P1 and T2 by T1 will be less than 1. So it means that flow properties actually are changing, these are actually decreasing. So density, static pressure and static temperature are decreasing, and on the downstream of the expansion fan these will have less values in comparison to upstream flow situation. Okay, point number 3 is that the expansion fan will be formed by nothing but combination of these will be formed in between forward and rearward this expansion waves. Okay, so one will be having angle mu1, which will be sine inverse 1 by m1, and other will be having angle mu2, which is sine inverse 1 by m2. So infinite number of weak waves which are actually in between these angles mu1 and mu2, these forms nothing but an expansion fan. Number 4 is that through the expansion fan I will be having streamline, and these streamline will be having smooth and gradual variation. Okay, so if I have an expansion fan, through the expansion fan my streamline will be nothing but having smooth and gradual variation, whereas in case of a shock wave, first point is that Mach number decreases, whereas here Mach number is increasing. Second is density, pressure and temperature on the downstream of the shock wave increases, here it is actually decreasing. Third point is that shock wave is nothing but a single wave. Okay, here I will be having combination of infinite number of weak waves, and these will be bounded by angles mu1 and mu2. And fourth point is that in case of a shock wave, we are having nothing but discontinuity in the variation of properties. Here we are finding that we are having actually any streamline which is passing, that is moving in a gradual manner, and we are having smooth and continuous variation of the properties. The only difference is that a streamline which will be just adjacent to the surface, that will be having only discontinuity, whereas all the streamline actually these will be continuous. And ultimate point is also there that in case of shock waves we have seen that whether of opposite families or whether of same families, these are having opportunities to interact with each other. Okay, so here expansion fan will be in such a fashion so that for a sharp corner it is cornered at one point, so expansion waves are starting at the same point, but ultimately in the other direction it is diverging, and these expansion waves will never meet away from the surface. Okay, so now I will stop at this point and we will have further discussion in our next lecture.